Bueno, bienvenido. Okay, so this is me. I have forgotten.
English?
Yes, so Chuhu is around. So,
Okay.
so now we are more international than we were 2 years ago. So welcome back everyone to this new session of the this special session of the Chilean Probability Seminar, where we have a friend of all of us here visiting. This Pablo Ferrari, coming from the far away lands of Argentina. And he will discuss about the Poisson representation of Brownian images.
Okay. This more than the focus an exercise. So I was this orange thing is Brownian motion, and the blue thing is Brownian bridge. And this picture says that the Brownian motion, you take Brownian motion here and put this point here, all the points are going down here. Okay, so it's a deterministic relation. And I was curious how this deterministic relation comes from, and found some things that I didn't know, and will tell you what they are. So the first one is just the definition of Brownian motion. So it's a Gaussian process with independent increments, continuous trajectories, starts at 0, and has these covariances. So the covariances are coming from, so the covariance between the high at this point and the high at this point is just a measure of the intersection of the two points, like with white noise. And then there is the reconstruction of Brownian motion that is very nice. So you consider the dyadics numbers, k over 2 to the n, k between 0 and 2 to the n. So we are constructing the process between in times 0, 1. And then you take a family of Gaussian standard random variables, Zt and T belonging to this dyadics. So for 1/2, for 0, 1, 1/2, 1, 4, etc., you have this family of random variables. And then you construct the sequences, the sequence of functions going from 0, 1 to R. And the first one is simple. You take your first variable, Z1, and then you go take the interpolation between 0, 0 and 0 and 1, and 0, 1, 1, and 1, 1. Okay? And this is your first function. Then your second function is you take 1/2 of Z 1/2. Okay, it's 1. Okay, and then here is you have the sum of the first and the second function, and the third function you take in the dyadics 1/4 and 3/4. You take 1 over square root of 8, I guess, and of these two variables, and then you have this second function that will be this minus the previous one. Okay, so here you have the sum of these three random variables, and it's very well described. This is the reconstruction, very well described by Perez and Mortars, and here it is. So the first, so the Fn of t is what I just described. For t is in the dyadics of length of n dyadics minus the previous one that you have used. Okay, and then before between those you have this linear between consecutive points. So this is linear interpolation, and then you define dt, that Brownian motion at time t, as the sum from n equal to 0 to infinity these functions. Okay, the incredible thing of this that I discovered very recently is that if you move your Z1 here, all this construction moves together because you didn't move all the. So this is the experts in Brownian motion saying, yes, chocolate for the notice, no? But, this I discovered very recently, but this gives you a dependence of zero of that is independent of what happens in the middle in this construction. Yeah, so this thing is that B1, so Z1 is independent of the other functions for n equal to 1, because B1 enters only in F0. Okay, so then Brownian bridge. Brownian bridge is Brownian motion conditioned to have to arrive at 0 at time 1. So the formal expression is that you get a test function phi depending on the trajectory. And so BB I will call the Brownian bridge. B is Brownian motion, so you have a function of the trajectory. It's the expected value of that function, but conditioned to B1 equal to 0. And okay, so this maybe is you are conditioned to set that has probability 0, but the Levy construction of Brownian bridge gives you immediately the Brownian bridge if you don't use sum 1 instead of 0, you sum 0 instead of Z1. So you take F0. So if you do that, then Brownian bridge is just instead of starting from 0, you start from 1. And then immediately, since starting from 0, you have BT, so this is BT minus F1T, so you have that this relation that in principle is in log relation, this is almost sure relation between projects. Okay. So this is a curve. These are constructed, so BT and BBT are constructed in the same place, in the same space. That is the space of this independent Gaussian random variables. So this is a coupling between these two objects. And then since you have that, you can easily compute the covariances using, well, you divide that and have the covariances, and then you get the covariance of BT, BBT, and BBS if the minimum is T minus S times T. This is just an exercise, so we will not do it for you. Then the other thing is that you have an almost functional central limit theorem. That means that the trajectories of Brownian motion, the trajectories of Brownian motion can be approached by trajectories of triangular arrays of independent, identically distributed symmetric random variables. And so they are centered, then centered, so you sum empty random variables of the array number n, and then divide by the square root of n. And you have the Donsker theorem tells you that this converges in distribution to Brownian motion, and then using the Skorokhod representation, Breiman, but before they proved that you have also the supremum of the difference between this discrete approximation and the Brownian motion goes to 0. This is a comment here. When n goes to infinity. Okay. I will use something similar, but not for independent random variables, but for the point processes. Well, the first thing to introduce here is this Bernoulli process. So Bernoulli process is you fix an n, so it's parameterized by the number of points. I will consider it only in the interval 0, 1. This is the interval 0, 1. And then you consider a sequence infinite sequence of random variables that are called AI that are uniform in this interval and independent, and construct the point process is the point that consists of the first n positions of these random variables. Okay, so if you want to construct a Bernoulli process that we call AN, Bernoulli process in 0, 1, for n is equal to 4, you have for each line here 1, 2, 3, all the numbers, you have one uniform random variable. And so you go up to 4 and then project them in 0, 1, and then you get your Bernoulli process. Yeah. And this Bernoulli process is associated to the empirical measure that I will compute only in the interval 0 t, or for t in 0, 1. So L n t it will be I will give a weight 1 over n to each point. So and then I sum the number of points that are below t. So for instance, if t is here, I will have 2 over 4 for Ln of t. For this t, and then t here it will be just 1, and here it will be 4. Okay, in Poisson process, I will give you straight away the construction of the Poisson process. You take a Poisson random variable y lambda with parameter lambda, lambda is positive lambda. The probability y lambda equal to k is just Poisson. And I will take it independent of the vector of the independent IID uniform random variables. So, and then the Poisson process, I will call it C lambda, that will be A of y lambda. A was the Bernoulli, but so will be a Bernoulli process, but with a random number of points, and this random number is Poisson, so will be A1 to A y lambda. And here you have the construction of that. You simulate first yn equal to 6 in this simulation, and this gives you just cut your uniform random variables and then project them to get AIN, that is a Poisson. So in this way, you have immediately a coupling between the Poisson process and the Bernoulli process with n variables. And I call the Poisson empirical measure the same, but now you sum over this random number of points. In general, the Poisson process, you have a measure, mu, in some set. In RD, for instance, you have the Borel sets of RD, and then will be a family of random variables indexed by the Borel sets of RD, and then you ask that the n of f is a Poisson random variable with this mean, and n of f and n of g are independent if f inter g are empty. And here you have, for instance, if you are in R, you have two sets that are intervals here in this case, and then you have independence here, but if they intersect, the covariance between NF and NG is equal to the measure of the intersection. These covariances are the same that you have for Brownian for the bridge. In our case, we are taking mu, the Lebesgue measure, and consider sets only 0t. This is the reason that was so simple, the definition in the previous transparency. Okay, now you have this automatic coupling between Bernoulli and Poisson. You have your AI independent uniform random variables. Yn is Poisson with mean lambda. Bernoulli goes from A1 to AN. Poisson goes to A1 to AYN. And here you have the empirical measure for the Bernoulli, the empirical measure for Poisson. So, and the difference is the number of the AIs, which I goes from N to YN, that would be, is a signet sum. Okay? This is very difficult. So here you have the picture. So the Bernoulli are the projection of this thing. It's just reflect the fact that there are more common points than non-common points. The non-common points are the points that are going between N and Yn, and I put them in red in this case because Yn is smaller than N. Yn is a Poisson variable with mean N. So you have here represented the common points, and here the points that belong to the Bernoulli, but do not belong to the Poisson, but could happen the otherwise around. So when you project, you will have most of them are common, and some of them will be non-common. In this is the case when Yn is bigger than Poisson. The situation is very similar. The common points are all these blue, and these green points are the excess points given by the Poisson when Yn is bigger than N. Okay, now I call this Poisson walks. That is just the martingale coming from the Bernoulli, from the Poisson process, from the empirical measure. So you take the empirical measure of the Poisson process minus the expectation up to time t. So the empirical measure up to time t minus the expectation. And remember that this has the mean of this is exactly t because it's normalized by 1 over n, the mean of n of n. Mm-hmm. So when you multiply by n, this should converge to the Gaussian random variable. That this is what we are going to do. So so here you have the point. So this Poisson walks goes linearly at speed -1 down, where speed 1 down, and then jumps at each point of the Poisson process. And finish at some point that is B1. In this case, I am taking Poisson process 6. So you are divided by these are 1 over 6. And this should converge to 1, but then I multiply by square root of 6. Okay? So 1 over n times number of Poisson points until time t minus t, all of these multiplied by the square root of n. Okay, then you have that the Poissonian walk converges to Brownian motion. You have the rescaled walk is this one, and then Koshnerizan, I learned recently, but this is in the book of Korsok and read it, that there exists a family of couplings Bn and B. This is the Poisson, this is Brownian motion, in such a way that Bn are the Poisson rescaled walks, and the supremum of T of the difference goes to 0. I don't know if you know this. I look a bit like how it is done, but I have to study this result. But we need that. This is, in fact, this is inspired in score of embedding that is well known, and then Breiman using that proving this result for the random walk, for instance, that I mentioned before. And here the observation of this thing is that if you take a Poissonian bridge, so you condition that the Poisson walk arrives to 0, this is the same as, so you define it this way, the same way as before, but B1n, so the Poissonian walk is 0 if and only if the number of points in 0, 1, this is an n of 1, I forgot to. The number of points is exactly n, because you are dividing by n, then this will take out. But this is just the Bernoulli thing, because if you take the Poisson and condition to have exactly n, then the Poissonian bridge is exactly the Bernoulli walk, because the Bernoulli walk will come back to 0. Okay, then using the same construction as I mentioned, Nevisan, you prove this, the Brownian bridge also converges, almost sure. Okay, now you couple the Poisson walk with the Brownian bridge. Okay, we saw the Poisson and the Bernoulli is that. So here are the empirical measure of Poisson, the empirical measure of Bernoulli, and the difference between the Poisson walk and the Bernoulli walk is exactly the square root of n times the number of AI at time t, number of the AIs that are between n and square root of 3. Is exactly so. You have this coupling. So I am taking 6 points for the Bernoulli. So this will be the Bernoulli jump, and this is when you have less Poisson points than n. You have 4 Poisson points. Yeah, and here you have 8 Poisson points. So when you have 4, you go to B1, 6 is below. When you get 8, you go above. This. And then when you take limits of that, you get B1. This is just the ending point 1. So the M1 converges to B1 almost surely, because just a Poisson thing. And the difference, this difference converges to the number of points that are here, but the number of points that are here is essentially B1, that is this limit, because you are dividing by that, times B1 times the square root of n, multiplied by the probability that the uniform is less or equal than t, so this will give you B1t. Okay, so taking the limits, and you get that the limit BBN t is equal to the limit of BNT minus TB1, and this is another proof of that. So the observation is that is here that instead of moving the whole thing of the Leddy construction, here you have an extra number of points that is uniformly distributed on time. And the piece that you get, that is smaller than t, is of order of t times the square root of n b1, that is the number of terms of the difference. And this whole thing, when you divide by square root of 1, just goes to a constant. So you are incrementing from the beginning to the end in this construction, instead of moving the whole thing up. Okay. At some point, I arrived in the book of Sorgo and Revets to this formula by Kak. Said, no, this was proven by Kak 18 years ago, but he didn't write exactly. This he didn't get exactly what I am telling you here, because he just say, well, you write a Brownian motion like I did. This is my notation, not his, no? But this is what he wrote in his notation. And then he multiplies by, no, he sums and subtracts this term here. And so you have a square root of n divided by n, square root of n times this, and this, since this is a Poisson thing, this has yn points. So this converges to Brownian bridge. this converges to 1 because Yn is no, it should converge to 1. See, because this converges to 1. Yn converges to 1 because it divided by the square root of it. And this part is just the Brownian motion, but times t at time 1. Okay, this is all I wanted to say. Maybe I need to pass.
Are there any questions? Either in this room or in that room? In some room.
Yeah.
¿Tienes idea de la velocidad de convergencia?
Hay,
Diferencia de la...
hay, sí, hay. Hay resultados.
Eso va a depender del cable. El cable mejor es que otro.
Va de la Corojor Representation. Hay una de... bueno, está en el libro de Sorwes Reveche. Hay una serie de resultados. Y después hay un Keller, creo que se llama, que tiene un review en Probability Survey con toda la Corojor Representation.
So on that terms, so there is a really nice coupling between random walk and Brownian motion, in which the distance, instead of being like of order square root n,
Yeah.
it's like order of log n or something
Sí.
like that. So is there some story here where you can get like a really good?
I didn't explore that yet. No, the idea here is to give more physical reason more than a mathematical, because a mathematical prove it beautiful, no? That you can just move, but it's not really physical because and here you have that this increment you are constructing during the time interval, putting a bit at each time in this representation.
An adapter.
Yeah.
Are there any further questions? See the chat. I don't see where the chat is. No. I chat overwhelmed me. So if not, let's ask.
The fact that the point process was uniform.
No, doesn't. No, this is just to.
Yes.
No, you can do it.
You can prove por Mogoros Mirno.
Yeah, yes.
Converges.
You can do any measure.
There is no surprise with the sigma fields.
No.
No, because there is something with the sigma.
Sí, porque la presentación del Browniano del puente no es Markov. Tiene razón. El BT menos TM1 no es Markoviano. Tiene información del futuro.
Ah, sí.
No, pero sí, es marcoviano, porque sabéis que termina en cero. Te queda un puente Markov.
Te queda un puente, sí.
Queda un puente
sí.
Markov.
Pues,
No,
sí. Sí.
Condicional del punto era un puente. No es
No es
homogéneo.
la filtración de B.
Ah, no es la misma filtración de B, no, otra filtración.
Sí,
pero es marcoviano respecto a sí. No es marcoviano respecto a la filtración de
Porque
B.
el puente Browniano es Markoviano, pero esa representación, la filtración de B no es Markoviano.
Ah, es.
Pero esta construcción se llama.
Después de las
Claro,
filtraciones
la
pueden venir
construcción
algo
puede
de
ser
construcciones.
más Markoviana.
Pueden venir algo.
Pero
Tiene razón.
Pero si sumas todas las F menos la primera, te queda marcoviano porque vas explorando la
Claro.
gaussiana. No, más o menos. Gas. No, es así.
Porque en el primer término tú ya sabes.
No, porque,
lo que
no, porque hay
está-
parte, estás sumando. No,
No, porque en el primer término.
no porque vas sumando una variable que la vas a ver después.
Se me va pasando,
Sí.
A lo mejor por eso puedes tener convergencia casi sin kilómetros. No sé. Que depende de la filtración. Depende de cuántas. No, porque tienes el browniano primero y construyes algo en función del browniano. Entonces, no. Entonces, en esta filtración no es forma. ¿Sabes cuánto es? ¿Tiene una referencia a ese que lo trae?
Están todas las referencias.
56. El simposio
En el libro puso esta demostración de Brownian,
Ajá.
la del paseo aleatorio. Este es el sorgo y redes. Está muy bien escrito, tiene muchísimas cosas y entre las cosas que tiene dice la cosa de hack que mencioné ahí. Tú también ya sabía que esto iba a funcionar. Acá, esto lo descubrí recientemente, así que no me lo pude estudiar, como es el de Koshnerizan. Desde del 93, sí, ya es casi 30 años. Bueno, después está el libro de Yuval y Mortars. Y después está Ross, que también que es un sistema de partículas que también tiene stopping times, y está este de Ruth. Y hay otro que no lo cité acá. Y acá está el Soroscott, que es el que descubrió la inglés.
No se nada de
Sí.
contigo.
Ross, pero es el té.
Sí.
Sí,
Sí,
es
sí,
así.
sí.
Sí.
Sí, porque trabajó con Eulalia.
Ah, mira, sí.
Sí.
Sí, 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 sí.
¿De qué tiene el boot?
Ruth no lo conozco.
Claro, está relacionado con tiempo de parece. No me puede tener pasión, exacto.
Bueno, yo que tengo unos minutos, voy a aprovechar qué es lo que me está interesando. Pues la idea es demasiado rápido. Estoy interesado en lo que se llaman las tablas de contingencia. En ese el cuadrado 0,1